In this second session of Six Sigma, I have to warn you a little bit. I'm going to get a bit more analytical here. After all, this is applications of statistics. We're going to get deep into the statistical concepts of Six Sigma. Most speakers or experts of Six Sigma focus on the management aspects, which is critical to achieving a Six Sigma objective. However, if we overlook the analytical aspect, then we'll be missing a lot, because without understanding the analytical aspect and the statistical concepts underlying Six Sigma, then you will be good in management aspects, but measuring things, measuring the opportunities, measuring the quality defects will become another challenge that you have to face. So in this session, our focus entirely will be on the statistical aspects of Six Sigma. Let's go to the slides. I guess the starting point here is how a process is shifted. And we mentioned a little bit in the last session about the shift of a process. And we use the car because it's a common example. Here is a car that's driving in the middle of the road or in between the lanes as specified by the lower and the upper spec limits. So this car is doing fine. Over time, as we mentioned in the last session, a car may shift. And in a Six Sigma process or in a good process or describing a good driver is the one that can actually either maintain the target all the time, but especially in short term, but on longer term, if he will have to, for one reason or another, to deviate from the target, he should not exceed his own lanes or his own boundaries, so he can shift a little bit but still remain within the specification limits. So that is the concept of shifting in Six Sigma. But that takes us back to what we covered early, which is the normal distribution. The underlying assumption of most of Six Sigma application is that the process sooner or later or ultimately will follow a normal distribution, meaning whatever the type of defects or whatever the type of quality characteristics, it will ultimately follow a normal distribution. And we discussed the characteristics and the attributes of a normal distribution. Specifically, we've learned how to calculate the area under the normal curve early on in previous sessions, or the percent of components that are within some values of the characteristic. In dealing with Six Sigma, we have to think of a normal distribution. And as we've always learned, in a normal process that has control or natural control limits at plus or minus 3 sigma, this process is considered normal. Now imagine for a minute that these are the upper and lower spec limits. Now if these are the upper and lower spec limits, which are almost coincided with the natural limit, that's the span or the width of this distribution, then if this process is to be shifted to the right, then we are in trouble, because a lot of this area is now outside the upper spec limits. On the other hand, if it has to shift sidewise, then we still have a great deal of components that are outside the spec limits. Let's take another look at this. Here is the process, here is the upper and lower spec limits. If the process shifts to the right, then now you see all this area here, the shaded area to the right, is the area that's outside the upper spec limits. All of this will be rejected, or all of this will result in customer dissatisfaction. Very good. If we go on the other hand and expand the distribution sidewise, that's variability within the process with the center maintained as is, then we see again that we have defects outside the upper and the defects outside the lower spec limits. We will call the first one, which is this one here, shift A type, or type A shift defects. This one here, we're going to call it type B. So you can distinguish between the two, because Six Sigma, although it's primarily focused on type A, but it will result in an automatic improvement in type B as well. Again, here is our process. And if we look at type B, we see a great deal of percent that's outside the specification limits as a result of the fact that this process has suffered high variability. To give you an example, early on the course of statistics, we gave you the normal distribution, and we also discussed with you the empirical formula or the empirical rule. And we said that according to the empirical rule, at plus or minus 2 sigma, we have an area of 95.46%. Now, if the process is running at plus or minus 2 sigma, meaning if these are the spec limits, if the specification limits are at the plus or minus 2 sigma, well, guess what? You will have this much defects per million. That's 45,500 per million defects. So 95.46%, although it's an impressive number, okay, but that leaves us with a 4.55% outside. So that gives us a huge amount, huge number of defects. If these are cell phones, then we have a 45,000 cell phones outside in the market that have defects in them, and we will have 45,000 or more customer complaints. And you can imagine what's associated with that. Customer complaints, service or tech support, people are dissatisfied. I mean, it's a huge effort and a huge problem. Now, if we go to 3 sigma, now we notice that at 3 sigma, we told you that the empirical rule tell us that at plus or minus 3 sigma, we have a 99.73%. Even that, which cover almost the entire curve, okay, will be associated with 99.73 within and 0.27% out. So if the specs limits are the plus or minus 3 sigma, we still have 0.27% out, and that is, believe it or not, 2,700 or 2,700 defects per million. So that is 2,700 cell phone, 2,700 laptops, 2,700 TV that are or did not meet the customer requirement or the customer specifications, and that's a 2,700 tech support calls and a 2,700 headache. Now, if you go to 4 sigma, things are getting better, because at 4 sigma, the area under the curve, at plus or minus 4 sigma, is 99.9937%. But even at that, with the much smaller percent of 0.00633, we still have 63 per million. If we can achieve that, that would be fantastic. And so on. Now, if you go to the 6 sigma approach, we are talking about 99 point, how many nines here? 1, 2, 3, 4, 5, 6, 7 9%. And that leaves us with almost 0.002 per million defects, which is almost 0 defects. Now, I'm not saying that any company can reach this level easily. But again, it depends on the type of product, as we mentioned, the organization repetition, and the trade-off between cost and the value. Let us now move to the other type of shift, which is shift A, which is a common shift. In short-term process, this is what happened. The process is within the spec limits. But long-term wise, and let's just say that this is Z sigma and this is Z sigma. This is like plus or minus 3 sigma or plus or minus 6 sigma, and we will use examples in a minute to illustrate that. In this case, if the process is shifted to the right, okay, it will be shifted by a certain amount. If it is shifted to the left, it will be shifted by a certain amount. And that amount, let us call it delta sigma. Okay? And in either cases, we have defects. So you can see that type A process shift will result in some defects in both cases here, whether you are shifting to the right or shifting to the left. Now with this general view here, let us take a 3 sigma process and the 6 sigma process and analyze each to see how the effects will change if a process is allowed to only move within 3 sigma or a process is allowed to only move within 6 sigma and is still maintaining itself within the specification limits. Very good. Here is a 3 sigma process, and you can see here that this is a normal curve and the expansion here is 3 sigma to the right, 3 sigma to the left. Now if we have 3 sigma to the right and the 3 sigma to the left, okay, then the specification limit will be at 6 sigma. We are talking about a specification limits that coincide exactly with the natural limits of the process. So if this is a 3 sigma process, then the upper and lower spec limits will be exactly at the 3 sigma to the right and the 3 sigma to the left. Very good. So if we shift to the left, for example, we will see that we have defects. If we shift to the right, we will see that we have defects. And both these defects are of type A. Now, if we go back to the 1.5 sigma, which we mentioned earlier, and I'm going to tell you again the story of 1.5 sigma in a minute, then when you shift from the center by 1.5 sigma, what is remained for you here? Well, this is all 3 sigma span. So 3 sigma minus 1.5, then you are left with 1.5 sigma. Which means you are, at this point, is left with 1.5 sigma, and you are at a distance of 4.5 sigma from the upper spec limits. Very good. Now if we go to the 6 sigma process, which is 6 sigma to the right, 6 sigma to the left, meaning the upper and lower spec limits are at the 6 sigma process, then what we have here, if we shift the process to the right or the left by 1.5 sigma, the story will be different. Because at 1.5 sigma shift to the left, what we have left here is 6 times 1.5, and what we have is 4.5 sigma allowance that you can move in and still maintain yourself within the spec limits. And as you go to the right, you have plenty of room. You have 7.5 sigma. It's very important that we compare these two situations. The situation of 3 sigma with a room of 1.5, a room of 4.5, and the situation of 6 sigma with a room of 4.5 and a room of 7.5. And the idea here is to allow yourself a bigger space in which the process can shift yet remains in or within the specification limits. That's the only way you're going to produce a minimum defects. That takes us to the normal curve, and it takes us to how we find the area under the curve, which is a very important issue. So we have to learn that. Okay? In a 3 sigma process, for example, and we told you a minute ago, if you shift 1.5, okay, that means Z will be, suppose that you shift into the left, that means Z will be at minus 1.5. If you shift to the right, the Z here will be at plus 1.5. In either cases, to get the area, if you recall from the normal curve session, we go to the normal table, and since the normal table will give us the cumulative area, which is this green area here, then we look at 1.5 Z, and we find that the area is 0.93319. Now this is the area from minus infinity to Z equal 1.5. And what does that mean? It means that red area here of defects is 6.881%. That is if the process is running at 3 sigma. Now, what does that mean? It means in 100 items, you have about 6.6, about 7 defects. But this also means that if you are selling 1 million items, then you have over 66,000 defects per million items. And that is huge. Now, if we go on the other hand to the 6 sigma process, where we can shift by 1.5 sigma and have a 4.5 sigma allowance, meaning Z will be minus 4.5 sigma to the left or the right. Now the area here is different. At 4.5 sigma Z, the area under the curve will be 0.9999966. In fact, in most standard normal tables, you are not going to see a value at 4.5 sigma. Most statistics books stop at about 3, maybe 4. But look how large this area is. And what does that mean? If you subtract this from 1, you will have an 0.00034%. So in 100 items, you have almost 0 defects. And in 1,000,000 items, you will have 3.4 defects per million. And that is what Six Sigma is all about. In summary, here is a table where at different shifts, 1 sigma, 1.3, 1.6, all the way to 3, we just calculated this area here, and we came up with a value of 6,811 per million. And we also just calculated the 6 sigma shift, and we found out that's 3.4 sigma. Why 1.5 shift again? Well, as I said earlier, the story of 1.5 sigma began by Motorola, determining through years of process and data collection that processes can vary and drift over time, what they call the long-term dynamic variation in the center of the process. This variation typically actually falls between about 1.4 to 1.6 sigma. Whether this should be made, which really give us the 1.5 sigma right in the middle here. Now, whether this should be made an industry standard or not, this is highly questionable. Some industries or some organization may decide that 1.5 sigma is too much of a challenge. But that's the standard value of shift A in a Six Sigma approach. In light of the above analysis, one can see that a Six Sigma process operates on the basis that if a product design is robust against changes, it can indeed withstand plus or minus 1 sigma or 1.5 sigma shift in its quality mean value and still remain within the specifications. We now use the process capability analysis to examine the capability of a Six Sigma process. Now recall that we discussed process capability analysis in previous sessions, so you should be prepared to understand the concepts that we are about to introduce. The process capability ratio, or the CP, was defined as the upper spec limits minus the lower spec limits, divided by 6 sigma, or really the natural span of a normal process, which is plus or minus 3 sigma. Very good. So as a result of that, our CP will be the upper spec minus the lower spec divided by the span, which is 6 sigma. Now notice we are putting the upper spec limit and the lower spec limit at a distance of 6 sigma to the right, 6 sigma to the left. Now if the process is entirely a 3 sigma process, which is this small process here, then you really cannot shift much. Now you still have a CP of 2. Why 2? Because if you add up this 6 sigma here plus 6 sigma here, that will give you 12 sigma between the lower and the upper spec limits. So the difference between upper and lower spec limits will be 12. And that will be divided by the span of the natural process, which is the 6 sigma, the 3 plus 3 here, and that will give us a CP of 2. Now let's look at process B. In process B, you really don't have any room. You see, process A at the 3 sigma is falling way within the plus or minus 6 sigma. Process B, on the other hand, or when this process is shifted sidewise, we see that we don't have room anymore, because at this point of time we have a process that's already expanded at the upper and lower spec limits to 3 sigma. And what does that mean? It means that the difference between upper and lower spec limits is 6, and the span of the process is 6, and that will give us a CP of 1. So you can see here that depending on how the span of the process and the specification limits, a process can be 2 CP or 1 CP. Now, when the process is shifted center-wise, then we have a bigger problem. Recall that we use in this case the CPK, not the CP. And taking that into account, the CP will no longer be useful. We have to move to the CPK. Why? Because the CPK accounts for the difference between the actual value and the target. I will use examples in a minute to explain these issues. The point to be made here is that a centered process, okay, if dealing with a centered process, then at 3 sigma, the CP will be 1. And of course, in a centered process, the CP and the CPK are the same. At 4 sigma, it's 1.33. At 5 sigma process, 1.67. At 6 sigma is 2. You can see the difference. If the process is shifted, shift A is to the right or the left, you can see that at 3 sigma process, we have CP of 1, just right, but CPK of 0.5. And we told you before that a CPK of less than 1 is not good. That indicates a process that's incapable. Now notice here at 4 sigma, CP is 133, CPK is 0.83. At 6 sigma, on the other hand, that's a 6 sigma process, or a process that allows to shift to the right and left to within a 6 sigma specifications. We have a CP of 2, that is twice as much the minimum requirement, and we have a CPK of 1.5, that is despite the shift. What we covered so far is basically some of the analytical techniques by which we can calculate the extent of shift, the area corresponding to that shift, that's the percent of components resulting from a shift of type B, which is the expansion, or type A, which is the shift of the center. We also discussed how we calculate the corresponding process capability coefficient, the CP, or the CPK, in which we account for the shift from the target. In the next session, we will give you some practical examples to elaborate more on what we covered in this session.